Hi, this is a project to use activated carbon together with ethanol to get cooling effect using adsorption, refrigeration, and solar thermal energy. Now, the solar thermal energy is not used at the time being because I'm just doing the experimentation on this system. The original system was done as an honors thesis by Joshua Romo, and I'm just trying to do the same thing with a little bit of twist here and there. I have set up my experiment and it's going to use the same idea. Now it is the effect of using activated carbon with ethanol. Now the project was done by the University of Dayton. This was part of a STAR project, STAR meaning solar thermal adsorption refrigeration. And it is using green refrigeration because it's using solar thermal energy. Now the electricity is not available all over in some parts of the world, so they're using available resources like solar thermal energy and so on. So it uses sustainable adsorption, which means that they use available resources, like for example activated carbon that has come from renewable resources, like you have coconut shell. And the motivation about it is that they try to use whatever they can to get this one done. So it was done in Patna, India, and you can see the refrigerator on the left side and the markup experimentation on the right side. The right side is the one that they done at Dayton. So they used activated carbon with ethanol, and it's used because it's non-toxic. Ethanol is non-toxic, and it doesn't affect the environment like CFCs. The idea is that to use ethanol is because it can go down to low temperatures like -5 degrees centigrade, and it's a good fit, especially for the areas of the world that we can get activated carbon from. The experimental STAR system is shown in a picture here. You can see the bottom is the ethanol, and on the top is the activated carbon, and it's heated. The activated carbon is heated to get desorption, to get the ethanol back down, and it's we use ice on the tubing to condense the ethanol. So it's an activated carbon bed. On the top, you can see the picture here. The activated carbon is heated, and after heating, desorption happens, and the ethanol that has been adsorbed on the activated carbon is desorbed again. So it goes back down and it condenses back into ethanol. Now the formula for the coefficient of performance, or COP, is QE over QS, where Q is the cooling power and QS is the solar power. So because they use solar power, so the heat is between 60 and 95 degrees, and we get a COP of 0.3 to 0.7. And heat is applied to the adsorbent bed using the solar collector, and it's a quasi-continuous operation, so that you get adsorption in one phase and then you get desorption in the other phase. Now, before using the activated carbon, we have to use an oven to heat it up to make it ready, so that anything that is stuck on the activated carbon is pushed out, it's desorbed, and the activated carbon is ready to receive ethanol. This is an important step, and it takes like maybe a few hours to get the whole thing out, and the temperature should not go above 120 degrees. But it's done in increments every half an hour so that we reach that stage. So the adsorption itself is you have a top ball valve which is opened. So then what happens is that the ethanol is pulled into the activated carbon, the ethanol vapor, it flows and it absorbs on the activated carbon. As more ethanol is absorbed, then more liquid ethanol evaporates, and this evaporation takes away the heat from the ethanol, and the cooling effect happens, so that the ethanol on the bottom becomes colder, and that's how we get the cooling effect. Now this is the adsorption. So this is the phase one of the process where you have ethanol vapor going up. And then the desorption is the reverse of it. So what happens here is that we, because this is an experimental part, so what we do is we use ice to condense the ethanol back. So first the ethanol, the activated carbon is heated, and the ethanol evaporates again. To condense the ethanol, we use ice to lower the temperature and convert the vapor back into fluid. So now, of course, in desorption, we don't heat above 120 degrees because that will damage the activated carbon. And it begins to, also the ethanol will begin to decompose. Now, here we have 4 cycles that have been done to test and see the sustainability of this project. So what happened was that in the first phase, we got better results. And then we have the second and third and fourth phase. So these are the different cycles that we used to test the system, and what kind of temperatures we got. So we are going to do the same thing here, and we will have our own chart to show the results of our experiment. 4 cycles is a good way of showing how the system will work, because it has to be sustainable. It has to continue working on, and we want to know how good it will be on the long term. And especially with the different temperatures. As you can see here on the left, it's just a diagram showing that we get solar energy, and it's in the cold box down is where the ethanol is, and it's it adsorbs and desorbs back. So the conclusion is what they have done here, and they have used different types of activated carbon. They concluded that Cocoa Plus was the best type of activated carbon, which is made from cocoa shells and coconut shells, and the temperatures and the timings and everything was calculated, so that and the pressure also, the vacuum pressure is calculated, so that we get the optimal kind of refrigeration that is needed. And that's basically the system that we are going to do here, and I'll have videos showing what I have done. And thank you very much. Okay, now the videos will start in a bit now. So I'm trying to get the vacuum here. I open this valve. I have my pump. It's working. and I heated the water so that I can see the water boiling. It's not hot, it's about maybe 35 degrees, and I can see bubbles forming, which means that there is vacuum happening. I'm just checking my vacuum if I'm getting enough vacuum. Yeah, I can see bubbles going up. Yeah, it looks good. Okay. Waiting for more bubbles. Looks like small bubbles are forming, and this is a good sign. Now, I have a problem with my pump that I'm getting oil coming out of it. So this indicates that my pump has a problem. My compressor. The compressor, I'm using my compressor as a vacuum pump. So, but the oil is coming out, which is not a good sign. I have to check with the guy I bought it from to make sure that this is not bad. Okay, I'm not getting any more vacuum, so it looks like this is not doing much vacuum, or I have some kind of leak somewhere. I tried to close all my leaks, but there is definitely something happening here. Okay, so it should have been bubbling by now, but it's not, which indicates that there is a leak somewhere in my pipes. Okay, so earlier I had some leaks here. Most probably I still have some leaks here because this is coming out. Yeah, I have definitely some leaks here. Yes. Okay, so I'll stop the video here to try to fix this, and then we'll see how it goes. But there are bubbles, which indicates that some vacuum is happening. Okay, so we'll stop right now. Well, I found the problem. It's here because this pipe has a wider tip than here, so I'm getting a lot of space here. I can't fill it up with silicone. That's not gonna work. Well, I have to find either another pipe or some way to close this here. Maybe put a clamp here and it will close it off. A clamp might work because it's tight over here. So, and anyway, I'm gonna fill it up with silicone to see how it goes, and put a clamp here, and then I'll use this valve to connect it to the pipe, and this should do it because this has a smaller opening over on this side and a bigger opening on this side, so these are a better fit for my work.